Hello everyone, today we will have lecture 25. We have been talking on passivation. Today also we will continue our discussion on passivation. And in last few lectures we could find that in certain metals and alloys, when the metal is taken to anodic side, that means anodically polarized, its corrosion rate reduces to a great extent. And we could also see that the corrosion rate becomes constant over a range of potential, and also there could be spontaneous passivation, there could be active passive transmission, where the material can go to active state to the passive state. And then we started looking at another segment in the polarization graph, where the current density again starts increasing from the constant current density in a range of potential. That means, in the passive range, if we continue increasing the potential towards positive side, at certain point it starts increasing again, and there we could find that there could be a possibility of oxygen evolution, and we tried to connect this oxygen evolution with respect to Pourbaix diagram. And we have given one example of iron system, where depending on the pH one can have in oxygen evolution in all the pH, but if the pH is less than 7, the oxygen evolution is from a reaction where water breaks down and then forms oxygen and H plus ion with electron liberation, whereas if it is a basic medium, that means basic or neutral, that oxygen evolution still would happen, but here OH minus would form oxygen and H2O along with electron liberations. That means, both the cases it will be anodic polarization of oxygen evolution reaction, and we could see that yes, the current value will again further start increasing. Now, there could be other reasons for the increase in current density after reaching to a potential where constant current density is maintained. That means, after the passive range, the current density can again increase, and those increase in current density can relate to different other phenomena. So, we will try to understand those phenomena, why it happens. At the same time, in case of active passive transition, why the graph reaches to a maximum, that means I critical, and then it reduces and reaches to a constant current density over a range of potential. So, we would try to understand those kind of those situations also, why it happens. Now, if we try to see a typical polarization plot for the anodic process. So, if we consider this reaction, of course, this part is anodic and this is cathodic. Now, if we try to plot the anodic and cathodic both sides, let us say this is my IC corresponds to M my N plus Ne equal to M, this is a cathodic process. Then we would have anodic process, and it reaches to a maximum point. This is, let us say, the maximum point, and then we have found out that it starts decreasing, and then it reaches to a very low value, and then constant value is maintained, and then from here you can have a graph like this. So, this is the segment, this is I0, this is E equilibrium of that metal. All those specific points are IC or I critical. This is ECP or complete passivation. This point is EPP, is called primary passivation, and then of course this region we call it passive, and then this particular region active region. Now, in one instance we could see that when the polarization curve, let us say if this is my Pourbaix diagram of iron, this is the Pourbaix diagram of iron, here it is FeOH whole 3, this segment is FeOH whole 2, this is Fe plus plus, this is Fe plus 3, and this is H FeO2 minus. In that case, we have understood why this particular line appears. If we have a situation, if we increase the polar potential at a particular pH value, fine. So, this is E versus pH, and there we could see that it intersects with two reaction. So, this particular point corresponds to this where oxygen evolution happens, and in this case since this pH is, if it is, this is 7, pH is less than 7. So, reaction would be H2O O2 plus 4H plus 4E. So, this oxygen gas will evolve, and here we can have hydrogen evolution reaction. So, this particular, there could be another plot corresponding to this. So, this is nothing but E chord, and then we can have a corrosion plot like this. So, we have understood that. Now, if we try to see the polarization line corresponding to this line, and let me put some mark. Let us say this is A, this is B, this is C, this is D, and this is, and I am not putting any value. So, this is let us say F or DE, or since we have putting E as potential. So, let me put F. Now, if we go from A to B along the anodic polarization line, we are following a Tafel equation, which is neta anodic equal to beta A log of I A by I 0 of metal on metal surface. This is the I 0 of metal on metal surface. Now, when it goes there, so we are having this reaction. Now, if we take a simple reaction like M minus 2E equal to M plus 2, and if we take this particular M plus M, M can also have a reaction like H2O I can have this reaction. I can have this reaction also. Now, if we go back to let us say in case of nickel, we have seen that in case of nickel our polarization plot looks like this: nickel plus plus nickel NiO. Instead of NiO, instead of nickel I can put it as M2 plus MO. Now, this particular line corresponds to this line, this particular equation, which is potential as well as pH dependent. So, MO is, there is a possibility for the formation of metal oxide, and this metal oxide is forming as we are going higher, and so because we are taking the potential in the positive direction, because we are going in the anodic side. So, if we take the potential in the anodic side, so actually we are increasing the potential, we are increasing this reaction. At the same time, there is a possibility for the formation of MO. So, we have two situations: increasing situation case, this is two cases, M plus plus formation rate increases, because as we go along the potential axis towards positive direction, I have to increase the amount of metal ion formation, because that those potentials are decided by the metal ion concentration in equilibrium with the metal, like this here. So, as we go positive side, metal ion concentration has to increase, and since we are considering the plot between log I and E, so that means the I indicates the rate of the process. So, the rate of metal ion formation increases. Now, second part, since we are going towards positive direction, towards positive side, I am also having a situation of formation of having this particular reaction. So, when this reactions happens, again there is a possibility of, this is, and this is possibility of metal oxide formation. Now, if we compare the metal oxide formation, so that means Mn plus increases, concentration increases because of rate of here we are not considering N plus, N we have already assumed to be 2. So, here it is 2E, this should be 2 plus, the rate of this particular reaction increases. Now, this increase is reflected by IA increment. So, if we see this, as we go towards positive side, IA is gradually increasing along this line and governed by this equation, Tafel equation. Now, at the same time, if we have MO formation, and if MO form on the surface, of the metal, so we have a metal surface and these MOs are forming like this, locally those are nucleating and forming. Now, as we are going higher and higher polarization side, so I am seeing that MO formation, MO amount should also increase, because it is crossing this line, it is still further going up. So, if MO formation increases, so further nucleation of MO would happen, and at some point of time there could be a monolayer of MO that will form. Okay. So, this monolayer will cover up the metal surface. So, when it is in the beginning of formation, I can assume that along at a fairly large potential, we can start forming this one to be higher amount, at the same time this metal oxide formation. There could be metal oxide formation because of another reaction. So, this reaction is also possible. So, metal oxide is also forming. So, that means when it is start building up at fairly large potential around this region, I can have a kind of coverage of the surface of that metal by the metal oxide. Now, at certain point, so when it reaches to this, so that means this point indicates the boundary between this boundary we have talked about. In this case, this was the boundary we talked about in the last lecture. So, at that point I can have a complete coverage of the surface by a kind of monolayer or bilayer of metal oxide on the surface. So, we can have, when this monolayer or bilayers are forming, that means the surface is literally covered up by memo, and that will be the point where I could have this particular situation where acceleration of metal dissolution due to the anodic polarization is equal to the, by of course by this reaction, as a result of increase in E would be equal to the retardation of dissolution of metal by the same reaction due to the formation of oxide layer. Now, once we have this situation, this particular situation which appears at I critical, and I critical is nothing but maximum current density in the active zone. So, after that, since I have already reached to the, because I have crossed this particular boundary point, I can, if the process goes on, I will only have the situation of more and more formation of metal oxide. So, this particular thing can be stated as acceleration of metal dissolution equal to retardation of metal dissolution. But both the cases, the situation, this is happening because of formation of oxide layer, and this is happening because of the anodic polarization. Now, once we increase the potential beyond this I critical or corresponding to EPP, beyond EPP, if the potential increase, I could have a situation like rate of metal oxide formation exceeds the rate of metal dissolution. Now, when we have this particular situation, then I will see that after reaching this, once we increase potential little bit, since the metal layer is completely covered up by metal oxide and metal oxide is also amount of metal oxide is also increasing. So, it will cover up the metal surface completely and the current density start dropping, because now the dissolution of metal will be decided by the ion diffusion from inner surface, that means metal and metal oxide interface, to the outer surface, which is metal oxide and electrolyte. And at certain location, I will have a situation like steady state. I will have a steady state situation where the rate of oxide growth would be exactly equal to the rate of dissolution, which is nothing but I p, and this I p is I p or I passive. So, after crossing I critical, current density reduces because more and more oxides are forming on the surface, and at certain location the rate of oxide growth will be just equal to the rate of dissolution, and that point I will experience I p, and that point, potential point, will be called as E c p or complete passivation. Complete passivation potential. So, this is the steady state. Now, what happens? So, at I critical, the retardation of metal dissolution due to the metal oxide formation is equal to the acceleration of metal dissolution due to the anodic polarization. Now, after that, since we have already covered up the surface, metal oxide amount is increasing. So, it is covering up completely. So, actually metal oxide is growing, and when it grows at certain location, the growth of metal oxide, because of that reaction of metal ion with the environment, or because of these two reactions, this is one reaction, this is another reaction, these two reactions. So, we will have a continuous growth of metal oxide, and this continuous growth of metal oxide also, this metal oxide is also allowing this metal ion to move out from the inner surface to the outer surface. That means metal and oxide interface to the metal and oxide and electrolyte interface, and then it is dissolving. That means it also has got influence on the solubility of that metal oxide. So, metal oxide is soluble as per the solubility of that metal oxide at that particular temperature, it is dissolving. At the same time, it is growing, and that growth rate will be just equal to current density at I p, and that passivation starts. Now, beyond this passivation, actually I could see that beyond this passivation, my I p does not change, it is a constant current density, which is the dissolution rate of that particular metal over a range of potential. Now, what happens here? So, from, if I try to see from, if I try to indicate those points from C to D, it is called passive range, and there the oxide thickness increases. Why oxide thickness increases? Because it has to maintain this x is the distance and del E is the potential change. This is basically the electric field, and this electric field and this electric field has to be maintained constant over the entire passive range, this potential range, and that is what the thickness has to increase. And oxide thickness increases when it increases, at the same time this increase in potential tries to pull out metal oxide to the outside surface, but this increase in oxide thickness will maintain the rate of the metal dissolution constant. So, that is what the current density maintains constant at I p. So, we could understand what happens in this particular range. In this particular range we could understand now. Now, at this point if it intersects this, then of course oxygen evolution happens, but if it still, if we go farther positive side, and or it can happen below this oxygen evolution also at this point or at this point, where oxygen evolution is not coming across because of this cutting cross section of the oxygen line in the Pourbaix diagram, then there could be a possibility of transpassivity. How transpassivity appears? Let us see that. So, that means the graph, if we see log I and potential. So, I have this plot, fine. So, these are the plots, I am not indicating. So, this is I critical, this is I passive, and now instead of having oxygen evolution reaction, there could be possibility of formation of some complex metal ion, and there could be possibility of dissolution. Now, when it happens like that, that time this particular zone is called passive, this particular zone is called active, and then beyond this zone we call it transpassive. So, this I can write it as ETR, okay, which is transpassive. So, this is ECP, this is EPP, this is E equilibrium of M. So, now why transpassive appears, and this breakdown, there could be possibility of breakdown of that passive layer, and by before reaching to a higher potential the surface oxide layer can dissolve and the line can move this way, it can move this way. So, this is a breakdown. There could be possibility of it can go to a very high potential, and there could be possibility of formation of a porous passive layer which happens at a very high potential in case of aluminum or titanium. So, we will try to analyze these in our next lecture. So, let us stop here. We will continue our discussion on this transpassivity, breakdown of passive layer, or the formation of anodic formation of porous layer at a higher potential. We will talk more on this in the next lecture. Let us stop here. Thank you very much.